Okay, in this video we'll talk about some of the exercises regarding the previous introduction of DNF block element. So if you haven't watched the DNF block element introduction, please go and watch it, because we need a lot of electronic configuration, understanding electronic configuration to do all these exercises. So directly from your textbook, we have the exercise 8.1. we have the first questions. Write down the electronic configuration of chromium 3 plus, promethium 3 plus, copper plus, and cerium 4 plus, and all these ions. So I'll do some of the exercises regarding with this, and if you are able to understand it, I also encourage you to do it alone by yourself for the rest of the other ions here. So we have the first one, the chromium plus 3. It means there's a removal of 3 electrons here. All we have to do is remove 3 electrons from the actual chromium electronic configuration. Alright, so in order to remove here, I'm going to remove the electrons from the 4s first, and then I'm going to remove 2 electrons from the 3d. So we remove 3 electrons, and that will give us, so from here to here it will just remain the same: 1s2, 2s2, 2p6, 3s2, 3p6, and then I've removed 1 electron from here, so it will become 4s0, and then I've removed 2 electrons from this 3d orbital, so it will give us 3d3 electronic configuration. So just to shorten this electronic configuration, we can also put from here to here is argon. So I can also put argon, which is an inert gas, atomic number 18. So from here to here it's up to 18 in atomic number, and we have 3d3. So it's not necessary to put the 4s0 as there is no electrons here, so the electronic configuration of chromium plus 3 becomes 3d3. Alright, so let's take a look at the second one. We have the promethium. So the actual current electronic configuration looks something like this. It's long. We have plus 3, which means there's a removal of 3 electrons. So I'm going to remove the electrons from the s orbital. There are 2 electrons here in the s orbital. We're going to remove these 2 electrons and 1 more electrons from the f orbital. So I'm just going to shorten the whole electronic configuration. So from here to here is xenon, that is 54, and I've removed 2 electrons from here, so we're gonna get 6s0, and I've removed 1 electron from the f orbital, so it will give us 4f4. So this is the electronic configuration of promethium plus 3. Just note that I've been removing the electrons from the 4s in here in this case also, and here also in the 6s electrons. The reason I'm removing the electrons in the first s first here in this case of the chromium is because 4 is the outermost shell. So you always want to start removing the electrons of the outermost shell, from the outermost shell. So basically the valence electrons. So let's just say we have the nucleus here, we have the shells, and if the electrons are occupied in something manner, you always want to remove the electrons from the last shell. So the 4th shell is the last shell, so you have to start removing from the last shell. And the second thing I did was I removed the electrons from the d orbital here in this case. So right after the 4s comes the 3, so I'm going to remove here from this 3d orbital. The second one, promethium, I've removed the electrons from the s orbital, the first one, because this 6s, the 6 is the last shell of all of these orbitals here. So I've removed the 2 electrons first from the s orbital here, and then I removed the 1 electrons from here, from the 4f electrons. Just note that here we have 5, we have 6 and 4. So as you can see, some of you might have think that if we're trying to remove the electrons based on the shells, we have 1, 2, 3, 4, 5, and 6. So if you start removing the electrons from the 6th shell, then the next thing we have to remove is from the 5th shell, which which in this case we have to remove the electrons from here. But instead of removing from this 5p here, I've started removing from the 4f. And here's the reason why. As if you see the energy of the 4f and the 5p, the 4f orbital is much higher than the energy of the 5p here. You can see here we go from 5p goes to 6s, and we have the 4f. So as you can see, the 4f has higher energy than 5p. Alright, if it has higher energy, it actually means, take for example, we have a nucleus and 2 electrons are here. This is the first electron, the second electron. Alright, the first electron is close to the nucleus, which means it should have a lower energy. And the second electron is farther away from the nucleus, it means it has higher energy. We're talking about this. So if the electrons in the 4f have higher energy, then it must be outer than that of the one which is closer to the nucleus. So instead of removing the electrons from the 5p, which is lower in energy, we start removing for the 4f orbital in this case. So two things you want to remember when removing the electrons to get all of these ions here. The first step you have to do is start removing the electron. Start removing the electron from the outermost shell. First, that's the first step to do it. The second thing is you have to see the energy which has higher energy should be removed first. So here in this case 4f has higher energy than 5p, so the electrons in the 4f, even though it's lower in shell, here is 4, here is 5, we remove the electrons which have higher energy. So remove the electrons. This is the second step, alright? So remove the electrons which have higher energy. These are the two steps you want to remember when dealing with all of this electronic configuration. Once you have mastered these two, you'll be able to do with all of the electronic configuration in the periodic table. So no doubt here. So let's take a look at the cerium here. So we have this lone electronic configuration here. We have in the end we have the 6s2 and 4f and 5d1. So from here to here it's up to xenon, that is 54 in atomic number. So I'm just going to shorten it. So we start removing the electrons. Alright, so 4 plus means we have to remove 4 electrons. So we remove 2 electrons from this 6s orbital, which is the outermost, which makes sense. So it will become 6s0. And then we remove the electrons from the 4f, because 4f is higher energy than 5p here or any other here in this group orbitals here. So we're gonna have 4f0 again, and we also remove the electrons from the 5d orbital, which 5d has higher energy than 5p here. If you can see the above principle here, we basically draw according to the energy increasing energy order. So 5d is here, before 5d is 4f, and before 4f is 6s, and 5p here we go. So as you can see, 5d is much higher energy than 5p, so we also remove the 5d orbital. Alright, so what we have here is 5d0, or you can put it as xenon here in this case. So 0 0 you can just not put in the electronic configuration because there's no electron. Alright, so cerium 4 plus comes out, we have the electronic configuration of xenon itself. Let's take a look at the last one, manganese, and the actual electronic configuration of manganese looks something like this. Now mm2 plus means we have to remove 2 electrons from here, so we just remove from the outermost electrons first. So remember these two steps always. And so what we're gonna see is from here to here is argon. We're just gonna shorten it because it's up to 18 in atomic number. So Alright, so that will be the electronic configuration. Also note that you don't have to put this one, so it will become argon and 3d5. Alright, so try doing along the other ions and see if you can do. And let's take a look at the next question here. Why are Mm2 plus compounds more stable than Fe towards oxidation to their plus 3 states? So this question basically means why do Fe plus 2 wants to go to their plus 3 oxidation states more than that of the plus 2 oxidation, or to go to their plus 3 oxidation states. So if you look at the electronic configuration of plus 2 here, you have this. In the end, we have the 4s0 and 3d5. And if you look at the electronic configuration of Fe plus 2, we have 4s0 and 3d6. Now that if Fe plus 2 lose one more electrons, if they lose one more electrons from the 3d orbital, the 3d will be converted to 3d5. Is that right? So this will become Fe plus 3. Now they have lost one more electrons. Alright, now that we know that d5 orbitals are half filled and half filled are more stable, that is the reason why they want to lose one electron so much from here to get to the d5 orbital. That makes sense. Alright, so in the case of manganese, they don't want to go to the plus 3 oxidation states, because if they tend to move to the plus 3 oxidation state, they have to remove one of the electrons from the d orbital, which will make them 3d4, and 3d4 is not that stable. So plus 2, they want to be just plus 2 and not go anywhere else. So there you have the answer here. Fe plus 2 wants to go to the Fe plus 3. So they basically go to the Fe plus 3 more easily. But in case of manganese plus 2, they just want to be in the plus 2. This is why plus 2 is more stable than Fe plus 2. That's the answer. Let's take a look at the question 8.3. Explain briefly how plus 2 states become more and more stable in the first half of the first row transition elements with increasing atomic number. So this is the first row of the transition elements. We have from the scandium to zinc, and the first half of this will be from scandium to manganese. That is scandium, titanium, vanadium, chromium, and manganese. So the question basically says, going from scandium to manganese, why their plus 2 oxidation states become more and more stable. So if you look at the atomic number from scandium to manganese, their atomic number increases like this, from 21, 22, 23, 24, 25. And if you look at the plus 2 oxidation states here, you get their electronic configuration. We see that in the scandium we have 4s0 and 3d1. Titanium we have 4s0, 3d2. Vanadium 4s0, 3d3. Chromium 4s0, 3d4. Manganese 4s0 and 3d5. So as the atomic number increases, the D configuration also increases. Take a look at this. In the scandium, we have the D1 configuration, as this is 3D1, D2 as it is 3D2, D3 as it is 3D3, and so on. So as you go from the scandium to manganese, even the D configuration increases. And we know that D5 is more stable because it is half filled. So, and on going from scandium to manganese, they are approaching the most stable configuration. So, their plus 2 oxidation states become more and more stable as we go from the scandium. Okay, let's take a look at the 8.8. What are the characteristics of transition elements and why are they called transition elements? Which of the D block element may not be regarded as the transition element? So, what are the characteristics of transition elements? They have multiple oxidation states. That's the first characteristics. Multiple oxidation states. So take a look at the manganese here. We can have manganese plus 2, plus 3, plus 4, plus 5, plus 6, and so on. And the second characteristics is that they have partially filled d orbital. So as you can see, we did a lot of electronic configuration where there is a half filled or partially filled. It can be D1, D2, but the d orbitals are not filled completely. That is one of the characteristics. And why are they called transition elements? Is because they transit between the S block and P block we discussed. So if you want to go from the S block to the P block, you have to pass through the D block. So right here, this D block is known as the transition element. So right there. And which of the D block may not be regarded as the transition elements? These are, we discussed about the zinc, cadmium, mercury, the group 12 right here. This group are not considered as the transition element. The reason is because if you draw the electronic configuration, you will see all of them have fully filled d orbitals. So this zinc, cadmium, mercury, they have fully filled d orbital. So they don't have partially filled. That is why they are not regarded as transition element, though they are in the d block element. Alright, let's take the last one. And okay, let's take a look at the last one. Here we have the 8.9. In what way is the electronic configuration of the transition elements different from that of the non-transition elements? So it's basically talking about the other blocks like the S and P blocks. So the general electronic configuration of the D block elements, the transition elements, is something like this. We have the N-1, D 1 to 10 to NS 1 to 2. So N here represents the number of shell, so you can see there. And if you look at the other blocks like P and S block, you'll get to see that their general electronic configuration will look something like this. P block elements will look something like this, NS2, NP 1 to 6, or the S block element will look something like this, NS 1 to 2. That is their general electronic configuration. Also note that the F block elements will have the N-2, F 1 to 14, N1D 0 to 1, and S2. So these are the difference of the general electronic configuration of the different blocks here. So just to note that the other blocks don't have this, usually don't have these d orbitals there. Usually they don't have these d orbitals, and even though they have, their d orbitals are going to be completely filled. And so just let me write down here, the other blocks like P and S block don't usually have d block or d orbital, or even if they have, the d orbital are fully filled. So those are the difference between the electronic configuration of the transition elements that differs from the other non-transition elements. So, all right. So just to let you know, we'll do some theory class also, but right after the theory class, I'll also get to explain some of the exercises from here also. So hope to see you in the next session.